Okay, good afternoon. I will let Lucia give the intro to our speaker.
So, ciao Annalisa, hi everybody. So today we have the talk by Annalisa Citro online. So she is in the States. So she was here for Christmas, but she has to come back. So we organize online. It's a pleasure for us. Some of you, most of you know already Annalisa. She graduated here and got PhD here in Bologna, who is working with me, Michele Moresco, and Andrea Cimatti, and also Salvatore. And then she moved to the States for 4 years in Wisconsin, and to work with Herb, and also collaborating with Max Bettini. And now she just moved to Minnesota, working with Claudia Scarlata. She mainly work on spectral analysis of different kinds of galaxies, from ancient galaxies during the PhD, the thesis and PhD on just one jet galaxy, and then moved to study metallicity and green P with Herb, and now also with Scarlata using UV spectra analysis. So today she will speak about the metallicity analysis on a lensed galaxy at redshift 3.8. So Annalisa, you can start. You have 20 minutes.
Yeah.
Thank you.
Okay, so thank you for the introduction and for having me there. So today I am going to talk about this gravitationally lensed galaxy, a redshift 3.8. I will call it JO332 for simplicity. This is a paper that I am working on with the research group that I was working with when I still was in Milwaukee. So you might recognize some of these names in the list. And what we did with this galaxy, what we are doing actually, is to perform a spectroscopic metallicity analysis. So first of all, I would just like to start from the fact that this galaxy is a redshift 3.8 and it's gravitationally lensed. So I just want to briefly discuss why this is important. Okay, so on the left, you can see the famous cosmic star formation history plot, where of course we see the evolution of the star formation rate as a function of redshift. Sorry, I covered the label down there. This plot, I put it there just because I wanted to show you how far back in time we can look by studying this galaxy. So taking as a reference the peak of the cosmic star formation history, that of course is at a redshift of about 2. Our galaxy JO332 is a redshift of about 4. That means a look back time about 12 gigayears. So we are looking at the universe when it was still young. Now, it's very interesting to study galaxies that are at such a high redshift because, of course, they give us hints about what happened in the universe when it was very young. But the drawback is that these galaxies are very faint, and so it's hard to perform detailed spectroscopic analysis with this kind of galaxies. One way that we have to overcome this problem is to study gravitationally lensed galaxies. In fact, the lensing provides magnification, and this magnification makes the galaxies, of course, brighter. And so this allows us to increase the data quality and the signal to noise ratio of the spectra that we observe. So JO332 is one of these galaxies, and thanks to the gravitational lensing, even though it's very far away, we are able to perform a detailed spectroscopic study. So this is JO332 that you see on the left. That's a composite HST image. Of course, in this image, the central galaxy is the lens. This is an elliptical galaxy at redshift 1 that is lensing JO332, which of course is instead the arc structures that you see around the central galaxy. So we found that JO332 is magnified by a factor of about 20 by the galaxy redshift 1. And as I mentioned at the beginning, this is a spectroscopic analysis. So the data that we have for JO332 are VLT-XSHOOTER and the VLT-XSHOOTER data. And you see here, this is the rest frame wavelength range that we are able to cover with this data. And you see that it's a very wide range. So we go from the UV to the optical, which means that we are able to observe a lot of absorption and emission lines, both in the UV and the optical, to perform our spectroscopic analysis. Now, of course, since this is a spectroscopic investigation, I want to show you one of these spectra that we used to perform our analysis. In particular, I'm going to show you the most interesting one, the most important one, considering what comes next. This is the force to UV rest frame spectrum. So you see in black, it's the spectrum, in orange is the error spectrum, and then at the bottom you see the 2D spectrum. So I highlighted two features here in red. One is the carbon-3 doublet. As you can see, it's well detected, but the most interesting thing about the spectrum is that we are able to detect the oxygen-3 1666 doublet, which is right here. And this is important because the oxygen-3 1666 is an auroral line, which means that it allows us to study to derive the direct metallicity of JO332. And as I will say in just a moment, this is, of course, pretty interesting and important. So I'm just going to move to my next slide, where I'm just putting out there which are the three main highlights of our spectroscopic metallicity analysis. So the first one is related to the fact that we can observe the oxygen-3 1666 auroral line. And this allows us to derive the direct metallicity of JO332. Now, of course, the direct metallicity, as we all know, is the most robust estimate that we can have for the metallicity of a galaxy, differently from the strong line method, which instead relies on calibrations that are not always accurate. So having this line is very important. And let me say that before JWST, so when we started writing this paper, working on this galaxy, JO332 was the highest redshift galaxy for which we had the direct metallicity estimate. There are other galaxies at redshift higher than 3 for which we had this measurement, but JO332 was the one at the highest redshift. Now, of course, there are already a few papers that are written using JWST data, where the direct metallicity has been estimated for galaxies at redshift higher than 7. One little thing that I just want to point out is that, of course, for JWST, we are still in the early stage in terms of data calibration. So the results from JWST might still be affected by calibration issues. The second highlight is we, as you saw, are able to detect the carbon line and the oxygen line. And so we were able to study the relative abundance between the carbon and the oxygen, and place constraint on the carbon production sites, which means trying to understand if carbon is mainly produced by massive stars or intermediate mass stars. But I will tell you more about this in just a few slides. And the third highlight is that we performed also a spatially resolved analysis of the carbon emission. in JO332 in order to understand where the carbon is mostly produced inside the galaxy. So let's start from the first highlight. I just want to tell you a little more about this. So the metallicity that we find for JO332 is 8.26, and on the left you see the mass metallicity relation. So the gray curve is the local relation, the local mass metallicity relation, while all the other colored symbols are higher redshift galaxies, and JO332 is this pink star here. So you can see that the gas metallicity of JO332 agrees with the one of other high redshift galaxies. And it's interesting to see that the gas metallicity of JO332 is about 0.3 dex lower with respect to the local relationship. And we found that this kind of decrease is compatible with the scenario in which with the higher redshift, we have an increase of both the gas fraction and the metal loading factor of the outflowing material, which means how many metals are lost by the galaxy through outflows. So in particular, that red curve that you see there, those are models, analytic chemical evolution models by Sanders et al. 2021. And that red curve is a model that they realized by assuming a change in both the gas fraction and the metal loading factor. And you see that JO332 agrees very well with that curve. And so we think that something like this might be happening in JO332. So it's a galaxy where there is a lot of gas and it has a high metal loading factor for the outflowing gas. The second highlight is instead related, as I said, to the relative abundance between carbon and oxygen. And here I need to give you a little bit of background. So we know very well which are the nucleosynthetic processes that bring to the formation of carbon. Carbon is a primary element which is produced through helium burning. But even though we know very well what happens for the formation of the carbon, the temperature that is needed for this nuclear reaction to happen, the helium burning, is a temperature that can be reached by stars on a wide range of masses, which means that carbon can be produced both by massive stars and intermediate mass stars. And we don't know yet which are the major contributors to the carbon that we see into the ISM. Carbon might be mostly produced by massive stars, and in this case, it is released into the ISM through stellar winds, or it might be produced mostly by intermediate mass stars. And in this case, it is released into the ISM through the thermal pulses in the AGB phase. So there is kind of a degeneracy between these two scenarios that you can see in the plot here. So if you look at this plot, this is the CO versus metallicity. And if you look at metallicities higher than 8, you can see there is a lot of scatter. We will talk about this in just a moment, but you can see that there is an increasing trend of CO with respect to the metallicity. Now, this increase can be explained by both the scenarios that I told you about. If carbon is produced mostly by massive stars, then the trend can be explained by the fact that the stellar winds are metallicity dependent. And so as the metallicity increases, the amount of carbon that is released into the ISM increases. If carbon is produced mostly by intermediate mass stars, again, we can explain this increase by considering the fact that intermediate mass stars have longer lifetimes. And that's why they release carbon into the ISM with a delay with respect to the oxygen, which instead can only be produced by the most massive stars. And so starting from this delay, and because of this delay, the carbon abundance builds up together with the metallicity abundance, and we have that increase. So it's interesting to see the location of JO332 in this plot. You see that, of course, JO332 is the star here, and you see that JO332 has a very low CO ratio. So we think that the fact that JO332 is very low in CO, it's kind of suggesting that maybe the carbon is mostly produced by intermediate mass stars. JO332 is a pretty young galaxy. From the SED feeding, we derived an age of about 90 mega years. So we think that it might still not have a consistent population of intermediate mass stars that can release carbon into the ISM through the AGB phase. And so that's why the carbon is still very low. Of course, by looking at this plot, there is something that cannot be ignored, which is the scatter that you can see at any metallicity. And according to starting from the scatter, Berg et al. 2019 tried to understand where this scatter comes from. And they created the analytic chemical evolution models. And what they found is that the scatter is mostly related to three main factors. The first is the star formation efficiency of a galaxy. The second is the yield of oxygen from massive stars. And the third is the duration of the star formation episodes. So in particular, they found that galaxies that are very low in the scatter distribution at a given metallicity tend to have a low star formation efficiency, a high yield of the oxygen, and longer episodes of star formation. And so we think that JO332 might be characterized by these three characteristics. So this is, of course, a very complex topic. There are many other shades to this topic. I am going to tell you a little bit more about this in my final slide. But anyways, what I'm going to do next is to talk about my third highlight, which is instead related to the spatially resolved analysis that we performed on the carbon-3. So what we did was starting from the 2D force-2 spectrum that you see up here. And what we did was looking at the average continuum counts along the spatial direction of the slit. So we took slices, which are these vertical blue lines, slices in where the continuum is and there are not strong emission or absorption lines, and we averaged all the continuum counts that we could see. And what we found is this little plot on the right. So you might need to turn your head a little bit to the right to see what's happening. But as you can see, as we go from pixel 67, which is the bottom of the slit, to pixel 80, you can see that there is an increase on the continuum counts. So starting from this evidence, what we did was deriving basically two extractions in the slit that you see now are coloring here, a pink extraction, which is including the upper part of the slit, and a green extraction that is including the lower part. And what we did was overlapping these two extractions to the lensed HST image. And you can see what's happening down here. So you see that the green extraction covers the lower part of the arc, while the pink extraction covers the upper part of the arc. And as you can see in this image, the arc is color-coded with three different colors, the red, the green, and the blue. And we found that these three different color-coded areas correspond to three different areas in the source plane. And as you see from these two images on the right, that's the source, the galaxy in the source plane, you can see that the blue and the green color-coded area correspond to two more compact knots in the galaxy, while the the red area, the red color-coded area in the arc corresponds to a more diffuse region in the arc. So of course, going back to this image here, you can see that the green extraction is basically dominated by what is red, so by what is diffuse in the source plane, while the pink region is dominated by what is blue and green, so what is compact knots in the source plane. Now, of course, from the two extractions, we were able to measure the carbon-3 line. Of course, in the pink extraction, the carbon-3 was detected. In fact, we can already see that the carbon is detected here. You can see it from the 2D spectrum, but the carbon is not detected in the green extraction. So putting everything together, this suggests that the carbon is mostly coming from those two more compact knots than from the diffuse region. Now, of course, this is related to the fact that probably the two knots have different physical or evolutionary properties with respect to the diffuse region. Unfortunately, with the data quality that we had so far, we were not able to perform a more detailed analysis on this. But it would be very interesting, of course, to do so. I don't know how I'm doing with timing. I do
19.
have 19. Okay, so perfect timing. I do have my final slide already. I have some other things to show you if we still have time. But anyways, these are two ideas or projects that we are trying to develop, and I hope that I will be able to put into practice at some point. The first is what I just said. So we know that there is something interesting going on into the source plane and in a spatially resolved kind of way. And so it would be interesting to maybe acquire higher quality data in order to understand what is it that brings the carbon-3 to come only from the two compact knots and not from the diffuse region in JO332. And the other thing is related to the CO versus metallicity plot that I was showing you. I think that it would be very interesting now that we have JWST data to look at a galaxy that is so young that it doesn't have intermediate mass stars for sure. And maybe that would allow us to break the degeneracy between the two scenarios and understand what's going on there. So I think I am done, but if we have more time, I could show you something else, or I don't know, leave space for questions.
You have, if you want 4 minutes more, there is time.
Okay, yeah. So another interesting thing that I can show you here is still related to the carbon-3 emission. So basically, this is related to the equivalent width of the carbon-3 line. So on the left, you see this plot is the equivalent width of the carbon-3 versus metallicity. So we have here a bunch of data. The black ones are local data, and the colored points are higher redshift galaxies. And the two curves are instead the models that describe the evolution of the carbon-3 with respect to the metallicity. So JO332 is up here, and as you can see, it has a very low equivalent width of the carbon-3. It's about -3. Of course, the negative values here are related to emission lines. That's why these are negative values. And it's interesting the fact that JO332 has such a low equivalent width of the carbon-3. It's also lower if compared to this yellow point here. This is another galaxy that was studied by Baylis et al. 2014. It's a similar redshift with respect to JO332, but it has a much higher equivalent width of the carbon-3. So the fact that this equivalent width is so low is pretty puzzling, because JO332 has many properties that would bring us to think that it should have a higher equivalent width of the carbon-3. It's young, it has a high ionization parameter, it has a pretty low carbon over oxygen ratio. So all these properties should bring it to have a higher equivalent width of the carbon-3, which we don't see. So this is kind of a mystery for now. I just found in the literature that there is actually another galaxy that is very famous, is Zwicky 18. This galaxy is a nearby galaxy that seems to be in a similar situation as JO332. It has high ionization parameters, young age, low carbon over oxygen ratio, but still has a very low equivalent width of the carbon-3. So this is kind of a mystery that we haven't solved yet, but I think that it's pretty interesting and maybe to investigate more. Okay, I'm done.
Okay, thanks. Questions for the speaker? Let me find the online participants. 1 second. Okay. Questions for the speaker either from... Yes, let's go here first, Francesca.
Hi, Annalisa. So I have a question regarding the statement about the lack of intermediate age stars in your lens galaxy.
Yeah.
So I guess that you derive the age, the age that you derive is a luminosity weighted age, I guess. No?
Those are derived from the SCD feeding. The age is derived from the SCD feeding to the HST photometry. Yeah.
Basically, it's a luminosity weighted age.
Yeah, and I mean, I agree that, you know, here I said it's a 90 mega years, and I didn't write the uncertainty, but the uncertainty is pretty high. So I think that the best way to address if the intermediate mass stars are important or not would be to actually found a galaxy that is at a much higher redshift, so that it didn't really have time to produce the intermediate mass stars. So probably JO322 is still not the best candidate, sorry, to do that. I'm just going back to...
Find a galaxy actually higher than 6, because I think they are...
Exactly, yeah. So to...
Yeah.
in fact, our idea was to kind of find a galaxy that is kind of it's very hard, but at a higher metallicity, like a galaxy that is here in this region, and see if at a very high redshift and in this region, in order to see if the carbon is high or low, and understand if the intermediate mass stars are important or not. Yeah.
Carlo?
Annalisa, this is Carlo.
Hi.
Can you hear him?
Yes.
Okay.
Yeah.
So I wanted to ask you something about the source reconstruction. So you showed the properties of the source, and then you showed the 3 colors that characterize the source, imaging the source image. So what is the lens model that you use to go back to the source plane? And what is the uncertainty in the source reconstruction?
Okay, so so in order to answer this question, like because I didn't do it by myself, and so I think that I can tell you more. I just have to go back to the paper, because there was a specific model used and I cannot remember it off the top of my head. But let me just, I can go back to the paper and just like write it down in the chat.
Thank you.
Sorry about that. Yeah.
Yeah.
Question 20 statement from the
I couldn't hear.
Yeah, the magnification 20 was taken from that lens modeling there. On the stage now.
So this is the paper where the magnification 20 is coming from?
Yes, yeah, it's actually like the source reconstruction was done in this paper that I presented to you, and yeah, that's where the model that was used is where the 20 comes from. Yes.
Yeah, just to understand if it is a slack lens or if it is an interesting mass reconstruction. No?
I couldn't hear you very well. Can you? Sorry.
Lens reconstruction, source reconstruction using HST image?
Yes. Yeah, I just don't remember like the specifics of the model that was used, but definitely from the HST images, yes.
Assuming this reconstruction is okay, I'm not an expert, so I have no idea. But
yeah,
if so, should I think that those two clumps are like, I mean, are we looking at a merging system, or these two clumps are just substructure within the same galaxy?
Yeah, so we didn't investigate that, honestly. So I don't know if they come from if they're merging systems or if they are two clumps. We assumed for our analysis that they were just two clumps like in the galaxy, and didn't make any hypothesis on the merging though.
If you have some delimiter data like SMA or ALMA, whatever, you can see there is some dust obscuration in the center.
Can you?
She cannot hear. If you want to, you can come closer. You can come closer. I cannot move the mic.
There is some sub-millimeter kind of data like ALM or SMA. You can reconstruct it and see the emission of the dust. So it is possible that you can see a clump of dust in the center that is obscuring the HST emission. So it could be a whole structure, but with dust in the center, in the nucleus of the galaxy.
So you're suggesting like that the two clumps might be just dust obscured, like clumps of dust?
It is something that it has already been seen in this kind of galaxies. I think about Herschel Atlas galaxies. So you see these different clumps in HST, but when you look in the sub-millimeter, you see the nuclear part of a lot of dust obscuration.
Yeah, the only thing that I can say is that, of course, only on the not in a like spatially resolved way, like by looking at the whole arc, we were able to study the dust, and it wasn't high, like the EB minus V was only like 0.2 or something, but we don't have you know, the detections to measure the dust in the separate regions, unfortunately. But yeah, it might be. Okay.
Then I don't know if you can see in the chat, there is a question from Roberto. Looks like a short novel. Thank you very much. I might have missed this, but could you explain a bit more what kind of relative transfer models you use to convert light luminosity into abundances? In particular, how do you normalize to the hydrogen content, and how do you account for the fraction of oxygen atoms that are not doubly ionized? Thanks.
Okay, yeah, so basically, so normalized to the hydrogen content. So basically, that is something that I didn't say. This galaxy, so in our spectrum, we do not go down to the Lyman alpha to analyze the hydrogen content, but this galaxy was already studied in the 2008 by Kabanak et al. 2008, and they did have the Lyman alpha included in their data, and so we use the hydrogen abundance that they found, which was in logarithm. It was like the column density was 21.4. And the fraction of oxygen atoms that are not doubly ionized, we used the correction fractions from Berg et al. 2018. And so that because actually the thing here is that we were able to account for the oxygen one-time ionized or two-time ionized, because we have the XSHOOTER data and we have the oxygen 35007 and the oxygen 23727. But we needed to use the correction fractions to take into account the oxygen 3 times ionized, which might be present in this galaxy because we also see the helium-2 1640, and so which of course, as we know, has a very high ionization potential, and so we needed to take that into account. So we use those ionization correction fraction. I don't know if that answered all the questions. Okay. So in the meanwhile, I'm trying to like access the paper because I wanted to answer that question about the lensing model. but I will maybe, I don't know, send an email to Lucia so that she can give the answer, okay?
I have also a question about the shooter spectrum. You already mentioned.
Yeah.
So used to calibrate the model and
We well, basically, yes. We you mean we made sure that the calibration was consistent between the F-force2 and the X-shooter. Yes. I don't know if that's your question though.
yeah, how you use the shooter spectra also to do something else or only?
We used it, well, we used it for the gas metallicity, because of course the oxygen 31666, the auroral line, gives you the temperature, the electron temperature, but then you need the strength of the oxygen 23727 and 5007 to derive the abundance of the oxygen in different ionization states. So we used it for that. We used it for the dust extinction correction, because of course we needed actually for the dust extinction correction, we used the H beta and the H gamma, not the H alpha, because we didn't have it. So yeah, we used it for basically for the direct metallicity estimate. So it was very important that we had it.
And could you also look at the morphology also in the shooter spectra or of these two? We couldn't do that actually. From the X-shooter spectrum, we really I mean, let me go back to that slide. I don't know if I can. What is happening? Okay, here. So basically here you see you see the wavelength range for the X-shooter spectrum. That's actually, it goes down to the UV2. The problem is that we couldn't use not even the UV part of the X-shooter because at least for the continuum, there was no continuum detected, basically, only emission. We could see only the emission lines. So we were a little limited in terms of what we could do with the continuum, and yeah. Okay.
Mauro, last one.
Okay, if you go back to the plot with the carbon over oxygen versus.
Sure. Here it is.
Question. So I apologize in advance if my question is too naive. I see that the error bar in the carbon over oxygen abundance is quite large compared to the one that I barely see maybe in the result.
Yeah. Yeah.
And I see that sometimes this is not the case for other galaxies in this plot. Can you comment on why this is large, and if, since you mentioned that you plan to, or you hope to have better quality data, if you can reduce this error bar?
Yeah, so what I'm seeing, and actually I'm noticing it right now as we speak, there are the measurements, well, actually this is not even really true, but all the measurements, these diamonds here, they seem to have a smaller error bars in the CO. I think that, because you can measure the CO as you can see here from collisionally excited lines or from recombination lines. And I think that depending on, the metallicity that you have, it would be it's the weakness of the lines that is giving you that larger error bar, even though the lines are detected. But I would say that the main reason is just very simply the signal to noise ratio that we have and in the lines, honestly.
Okay, let me see. There might be a last one by Eros I've seen. What are the physical scales of the nodes emitting CO3, the C3 in the source plane?
Yeah, so here is you see it's 1 kiloparsecs. 1 kiloparsec. You see here, kind of this is the scale that can help you to see. So it's a little smaller than 1 kiloparsec, I would say.
Okay. Okay, that clarifies it. Okay, then thanks. I think this is it for today.
Okay.
And enjoy winter in Minnesota.
Yeah, thank you, thank you. Bye.
Ok, grazie.
Ciao Annalisa, dove sei?
Aspetta che
Ciao,
sto-
ragazzi.
Ciao, ciao, ciao.
eh,
Sta